So this is lecture number 2. This is a polymer chemistry review, and what we're going to be focusing on are starting materials and polymerization methods. So I have this graphic kind of described as a plastics tree. In order to grow a tree, you have to have a good root system and a strong trunk, and that refers to the raw materials that are used, so monomers and other additives, and then the polymerization to make polymers. Property enhancement is through additives and other materials that are added to formulations. Then we branch out through processing, fabrication, and then the thing that brings us all of the dollar value is the finished products. But we have to be able to understand raw materials, property enhancement, polymerization, processing, and fabrication in order to grow the plastics tree. So this is kind of it in sort of flowchart form. So when we start with raw materials, we're starting with oil, natural gas, coal, chemicals. These can also be agricultural products or byproducts. So then these materials are treated to get our monomers, and then our monomers are taken to polymerization. The polymers are then put into some sort of form. In other words, granules, flakes, powder, pellet, or liquid. Polymer or plastic resins then go on to property enhancement, and this is often through compounding and formulation. And what that means is adding things like additives and modifiers to enhance polymer properties. This can go around and around for quite a while, but some of the additives that are included are pigments and dyes. Color is very important to formulations. So is flexibility, heat stability or UV stability, and then strength. And so fillers are added for strength, cost reduction, and other special properties. From this kind of property enhancement loop, we go on to processing. And this is molding, extrusion, calendering, gasketing, making it into sheets, all that things, so that we can make it into a finished product. Oftentimes things like sheet or film or rods or tubes are considered secondary products because they're not quite the finished product, but they have to but they've already gone through some form of processing. So secondary products then go to fabrication through heat bending, thermoforming, blow molding, rotational molding to your finished product, whatever it may be. Starting material sources come from, these days, the majority source is petroleum. Remember, less than 2% of oil and gas is actually used to produce plastics. We also make things from coal and natural gas. Increasingly, we're making things from agricultural byproducts, and these byproducts include vegetable oil, sugars, cellulose, protein, and other byproducts like lignins or other waste streams, glycerol from, say, biodiesel production. So this is what a vegetable oil molecule looks like. This is called a triglyceride because this thing in the blue is glycerol, and then these 3 chains, tri, are attached to that glycerol, so triglyceride. This is an example of soybean oil. These double bonds allow us to do a lot of fun chemistry on it. This is castor oil, so it has the same triglyceride structure, but it has hydroxyl groups shown here in the backbone, which also allow us to do chemistry and make monomers for polymerization out of it. Sugars and cellulose are also used as either monomers or precursors. So here we have a monosaccharide, this is glucose. Here we have a disaccharide, and this is sucrose or table sugar. And then we have complex carbohydrates. So this is a polysaccharide, so multiple saccharin units. And this one shown here, I believe, is starch. Proteins can also be used. This is what I did my PhD work on, is using proteins for adhesives. Protein are polymers themselves. Their monomers are amino acids. You add those 2 amino acids together and you get a dipeptide, and then you can polymerize more of these to make a polypeptide. So this is actually a this is nylon 1 is what it is. They can arrange themselves into primary, secondary, tertiary, and then quaternary structures. The primary structure is the order of amino acids. The secondary structure is what sort of 3-dimensional structure they might occupy. This is an alpha helix. Then that tertiary structure is how these secondary structures relate to one another. So you have an alpha helix attached to a random coil next to an alpha helix. And then if you have multiple peptide units in a particular protein, that quaternary structure describes how they are related to one another. So here's our red structure, how it relates to orange, green, blue, etc. There are a variety of factors that determine polymer characteristics, the arrangement, in other words, order of monomers, the chemical structure of the monomers, degree of polymerization, and then polymerization method. So we're going to talk about structural units first. First we're going to define monomers, oligomers, polymers, copolymers, linear polymers, branched polymers, so that we all have a basic understanding of what Jean is talking about when she's talking about monomer, oligomer, polymer. So here's some basic terminology. And this is just in alphabetical order, that's why it's listed the way it is. A branched polymer is a polymer with at least one branch point intermediate between boundary units. So this is an example of some branched polymers, A, B, C, D. Specifically, A is a branched polymer. B is considered a star polymer because it has a center point and they branch out. C is considered a comb polymer because it kind of looks like a comb. And then D is a dendritic polymer. They kind of grow out from points like branches on a tree. A copolymer is a polymer derived from more than one species of monomer, so you have a monomer with one chemical structure polymerized with a monomer of a different chemical structure. And we'll talk about that more specifically in a moment. A linear polymer is a polymer with no branch points. It's just a straight chain. A macromolecule is another way to say polymer. Macromolecule just means a molecule of high molecular mass. And the structure is multiple repetitions of the same unit. It's macromolecule and polymer are often used interchangeably. A monomer is a substance, each of the molecules which can, upon polymerization, contribute to constitutional units in the structure of a macromolecule. What does that mean? The monomer is what gives you that repeat unit. You add monomer to monomer to monomer to monomer to make a polymer. An oligomer is a molecule of intermediate molecular mass. What it means is it's bigger than a monomer, but it's not quite a polymer. So it's a few units, 2 or 3, maybe 4. And oligomer is just it's kind of a generic term. A polymer, and oligomer really also depends on who you're talking to. From a protein polymer chemist, they might have 3 units and that might be a polymer. But to, say, a synthetic chemist who's making things of 1,000,000 molecular weight, those 3 units together are definitely an oligomer. So it really depends on who you're talking to. A polymer is composed of 2 or more monomers, so again, that could be an oligomer, to produce a long chain or a branched compound. So a polymer is a big molecule, like a macromolecule. And then polymerization. Polymerization is the process of converting monomer or mixture of monomers into a polymer, so making polymers. Monomers are organic molecules that contain at least one double bond or a minimum of 2 functional groups. So this is our backbone structure of polyethylene. So here we have 2 possible candidates for what would constitute monomers for polyethylene. So here's ethane, here's ethylene. Now, based on these criteria, a monomer is an organic molecule which must contain at least one double bond or a minimum of 2 functional groups. Well, functional groups. These ethane groups don't really react with anything, so those aren't really functional groups. These ethylene groups don't really react with anything, but there's a double bond present in this monomer. So in order to make polyethylene, ethylene is our monomer. It's a big clue if something has poly in front of it. Ethylene is the monomer, polyethylene is the polymer that you make from ethylene monomer. Copolymers are another thing that you can do to make different structures in the backbone and therefore get different properties. Monomers with more than one recurring monomer unit. So this is an ethylene unit, this is a propylene unit. And this is an example of ethylene-propylene rubber. And that's a copolymer of ethylene and propylene. Terpolymers, it's not typically a term that's used very often in industry, but this is something that has 3 different monomers present. So ethylene-propylene diene rubber is a terpolymer, so 3, ter. This is also known as a copolymer, and is often not, the term terpolymer is often not used in industry, but this terpolymer has ethylene, propylene, and then a diene component to make this 3 different repeating units within the polymer itself. Copolymer design can give you really interesting properties in the resulting polymer based on how the monomers are arranged in the backbone. So here is some examples of that. A random copolymer is a copolymer in which the probability of finding a given monomer unit at any site is independent of the nature of adjacent units. So in other words, if I have A here, it doesn't necessarily mean I'll have B here. I could have another A, I could have another B. It's just random. But in alternating, it means that you have macromolecules that have two species of monomeric units and they alternate in sequence. So if I have an A here, there's always a B here. A, B, A, B. In a block copolymer, you have adjacent blocks that are constituentially different. I don't think I said that right, but in other words, you have a big block of A monomer, then you have a big block of B monomer, and then perhaps another big block of A monomer. And these can behave as a polymer blend rather than a copolymer. This is a graft copolymer, and the adjacent blocks are different, so in other words, B versus A. But basically what you have here is a backbone of one, so you have a backbone of A, with B blocks grafted onto it in branch points. So that's another type of copolymer structure. Some examples of copolymer are styrene butadiene rubber. So this is 25% styrene, 75% butadiene, and that produces a rubbery-like material. If you change those ratios, so in other words 75% styrene and 25% butadiene, you get K resin, and that's a very different, it's not rubbery, it's very different in its behavior. Acrylonitrile butadiene styrene is a copolymer. It's a terpolymer because it has acrylonitrile, butadiene, and styrene units all within it. You also have polyalumers, and these are block copolymers of propylene with small amounts of ethylene dispersed through them. You also have ethylene propylene rubber. Now this is a block copolymer, this polyalumer, with propylene and ethylene. Ethylene propylene rubber is different in that it's a copolymer. It has equal amounts of ethylene and propylene to produce a thermoplastic elastomer. These have the same comonomers, but the ratio and how they're arranged in the copolymer results in different properties. So this is a really good example of structure to property relationships. Styrene butadiene rubber, K resin, polyalumer versus ethylene propylene rubber. Same comonomers, it's just that different ratios of those and different arrangements give you different properties. Now there are two different types of polymer synthesis. There's chain growth and step growth. And in this lecture, we will refer to chain growth polymer synthesis. And chain growth itself is often referred to as addition polymerization. And you're just sticking one monomer on the end, you're just adding one block after one block. Step growth, which we'll talk about in the second portion of this lecture, and in the next video, is often referred to as condensation polymerization. So, in a chain growth polymerization, you have one molecule adds to another, and there's no net loss of atoms. In other words, you don't lose any carbon or hydrogen. Every atom that was present in the monomer is present in the polymer. You have very fast reactions. This requires an initiator to get the process of polymerization started. Chain growth has discrete steps: initiation, propagation, and termination, or chain transfer. You get very high molecular weight very quickly. So in this reaction, you have high molecular weight polymer and monomer, and nothing else. Monomer is present throughout because you need monomer to add to the end of the chain. And we have a longer reaction time. You get higher yields. In other words, more polymer chains, just not longer chains. There are different ways to start chain polymerization. And that refers to the species that you use to propagate the chain. So we have free radical. This is 50% of commercial polymerization. However, some monomers cannot be polymerized free radically, so you have to have other methods of chain growth polymerization. So you use a cationic polymerization, an anionic polymerization, or transition metal catalyzed initiators. So there are main differences between these types. Initiation. In free radical, you form a radical by a peroxide decomposition. In a cationic polymerization, you have a strong acid. In anionic polymerization, you most often use butyllithium. And in transition metal polymerization, you have a metal complex coordination. And the propagating species also differs. So this is what your end of the chain looks like. This is one electron, or a free radical, on the end of the chain. For cationic polymerization, you have a cation, or a positive charge, at the end of the chain. And then for an anionic polymerization, you have an anion, or a negative charge at the end of the chain. And then for a transition metal catalyzed polymerization, you have a monomer metal complex at the end of that chain. In free radical, these terminate a specific way. So in free radical, you get couplings of radicals. When two of those electrons come together, they form a bond. You also get disproportionation. In other words, you'll kind of steal a radical from another, and then it will terminate both chains. Or you'll get chain transfer, where something will, free radical will jump from one chain to the next chain. It kills one chain and the other chain keeps growing. In cationic polymerization, you can get rearrangement with the counterion. So what that means is your cation, your positive charge, will couple with a negative charge and then kill the chain. You can also get hydrogen abstraction from the active chain end to the counterion. That kills the catalyst. Or you have hydrogen abstraction from the active chain end to the monomer. So that also kills the polymerization. Anionic polymerizations are considered living, meaning they only stop when all the monomer is consumed. Now that's in a very, very pure situation. You have to have a very, very pure polymerization reaction for that to occur. But in theory, you can take an anionic polymerization, put it in a jar, stick it on a shelf, and then if you add more monomer, it will continue to polymerize. If it's very pure, that's what it will do. So that's considered fully living. And then transition metal catalyzed chain growth reactions can be terminated by adding hydrogen gas. So here are some monomers for free radical chain growth polymerization. So styrene is made into polystyrene, methyl methacrylate is made into polymethyl methacrylate, vinyl acetate is made into polyvinyl acetate, and then if you're going to make low density polyethylene, use ethylene by free radical polymerization. So ethylene can also be used to make high density polyethylene using different catalysis. Isobutylene, this is often used in synthetic rubbers, is what's most often used for cationic chain growth polymerization. And then ethylene, to make linear polyethylene or high-density polyethylene, is often anionic in its polymerization. And then propylene is what is most often used for transition metal catalyzed chain growth polymerization. So here we see the handy-dandy stop sign in the lecture. That is where I'm going to stop this video, and we will pick this up in the second part of this lecture video.